Hello class, welcome to lecture 1, What is Organic Chemistry? Getting Familiar with Carbon. So this is going to be one part of a two-part lecture for the first chapter in organic chemistry. And in here we're going to be talking about bonding and hybridization of carbon. This first lesson is primarily going to focus on what organic chemistry is and the importance of carbon in organic chemistry. So let's go ahead and get started. So first of all, what exactly is organic chemistry? You've certainly heard of it. You probably, certainly if you were in my general chemistry class, you've heard of it. Organic chemistry is the study of chemistry involving living systems, and particularly involving the atom carbon. So we're going to be very interested in carbon when we are dealing with organic chemistry. That's going to be the atom of focus, or the central atom that we keep coming back to. And living systems were originally thought to have some sort of a mysterious vital force that was bestowed upon these living systems that gave them special properties, and organic compounds, in comparison to inorganic compounds, they were considered special. This belief was held true until the discovery of what was known as organic synthesis in the 1800s. And organic synthesis is going to be a very big portion of this course. As we get into later chapters, we're going to talk about organic synthesis. Synthesis meaning to create, so we're talking about creating organic substances or compounds. So what exactly is it that sets carbon apart from the other atoms? So why is carbon important? Well, carbon is in group 4A, but what about 4A is special? The compounds in group 4A, and carbon is the most common out of that group, have 4 valence electrons, and each of those valence electrons are ready to bond to another set of valence electrons with a different atom. So since carbon is in group 4A, it's going to give it the ability to share 4 valence electrons for bonding. Now remember that when we talk about sharing electrons, we're talking about when we talk about sharing electrons, we are talking about covalent bonds, not ionic bonds. So hopefully you remember that. This leads to a variety of diverse chemical structures because carbon can bond to so many different things, and it has the ability to bond to 4 different things each time. So if you recall, the Lewis structure for carbon looks like this. We put an electron on each side of the atom before we continue and start pairing up electrons. So carbon has those 4 unpaired electrons. So let's take a brief review of atomic structure here. We're going to look at the nucleus, electrons, protons, and neutrons, and then talk a little bit about the periodic table and what's available there. So in terms of the atomic structure, on the left here you can see a general structure for an atom. And you see the nucleus pointing towards the middle here. The nucleus is the center of an atom, which contains both protons and neutrons. This is associated with the positive charge in the atom, and that's due to the protons that we have here, these little blues with the pluses here. The protons and neutrons are both found in the nucleus, and the nucleus is also what really gives the atom its weight. The electrons, even though they do have a weight, we consider their mass fairly negligible. The green with the minus charges here, these are the electrons. They surround the nucleus and they occupy the outer bounds of an atom in theoretical contained parameters that we call orbitals. So we'll talk about orbitals more in a second, but hopefully you remember from general chemistry we have s and p and d orbitals. The electrons fill up those structures or those parameters, and the electrons orbit in the orbital confinements. So that brings up a point. Remember that electrons, even bonded electrons, are not stationary, but they're really in constant movement with the orbital boundaries. So let's talk about what's on the right here for a second. We have carbon from the periodic table, and we have 2 things I want to point out here. First is the atomic number Z. That's that big number 6 up here. So anytime you go and you pull off a number from the periodic table with any given element, that's the atomic number. The atomic number is going to represent the number of protons as well as the number of electrons in a regular state that the atom would have. So the other thing I wanted to point out was the mass number, which is the one up on the right here. A lot of times that's referred to as A, and the mass number is the total number of protons and neutrons found in the atom. So we have AMU, atomic mass unit. And then when we get into doing calculations, a lot of times we convert the atomic mass unit over into grams per mole. And remember that when we deal with the atomic mass unit and all of the mass or atomic weights on the periodic table, we base it off of carbon. We take 1/12 of carbon because carbon is approximately 12, and we assign 1/12 of carbon's atom weight as the AMU unit. So hopefully you guys remember that stuff from general chemistry. So let's keep talking here. We've been talking about electrons and that they occupy orbitals. So this is going to come back into play here when we're talking about bonding later in this chapter, especially with hybridization. So hopefully you remember the electron orbitals. We have 4 types of orbitals that arise from the Schrödinger equation we learn in quantum mechanics. And those are the s, p, d, and f orbitals. And they increase in complexity as we climb up. So s is spherical, p is dumbbell-shaped, d is really sort of 2 dumbbells that are mixed together, and we have some other sort of funky-looking ones. And then f gets very complex when we get to that point. But we're going to really stop at S and P in organic chemistry. And I want you to think about why for a second. Why would we only do S and P in organic chemistry? So take a minute and think about it. Pause the video. All right, so hopefully you realize that the reason we primarily focus with S and P in organic chemistry is, number one, that carbon is S and P. It's in the quantum level 2 shell, and we only have S and P shells available. So because we're usually dealing with carbon in organic chemistry, we only really have S and P shells available to us when we deal with carbon. We don't have those D shells or those F shells. And a lot of the other things we're going to find that carbon ends up binding to or bonding to are going to also only have S or P orbitals for the most part. So we're going to really be concerned with S and P orbitals. You can see down here we have the S and P structure for carbon. We have S and then P, and we fill up the 4 valence electrons. So this would really be 2S and 2P if we're dealing with the valence shell with those 4 electrons there. So hopefully you remember the various quantum energy levels or shells. So when we have n equals 1, we can only have an S shell. That means there's only a 1s level. When n equals 2, we can have S and P, 2s, 2p. When n equals 3, we can have SP and D, a 3s, a 3p, and a 3d shell, etc. So if you are having any issues with that, you should go back and review some of your general chemistry. I also have videos up related to that material if you want to go and check that out. Just go to the quantum mechanics chapter. So carbon is found in the n equals 2, as we said. That gives it a set of S and P orbitals in its valence shell. Since S can hold 2 electrons and P can hold 6 electrons, these orbitals can fill to a total of 8 electrons. And 8 electrons gives us the well-known octet rule. So you can see 2 in the S here. If I were to fill each of these P's up with 2, I'd have 8 electrons in my outer shell. And everybody goes around, they always know the octet rule. Well, that's where the octet rule comes from. And not all atoms follow the octet rule. Some get away with fewer electrons, like hydrogen, and some can get away with more electrons if we have D shells available. But anything that only has an S and a P shell available is going to have to follow the octet rule, and that's where that comes from. So 2 electrons in every bond. That's going to be 4 bonds total around carbon for a total of 8 valence electrons, the octet rule. So let's go over and take a look at bonding involving carbon. Now this is going to get a little bit new. We did pretty simplistic structures when we were in general chemistry. So right here we're going to look at bonding with the atom carbon. So carbon, we've said, can normally bond to 4 atoms when it's in a neutral state. We look at that Lewis structure. It's got the 4 dots around it. Carbon often bonds with other carbons to form rings and chains. And that's really important because what we're going to see in organic chemistry, and there's a sample down here, we're going to see these long carbon chains that start forming. One carbon rides off another, it starts forming chains. And sometimes it can also form rings where it seals itself up like this, and it's sort of a self-contained carbon chain that forms a ring. But those 2 structures are going to be very, very common in organic chemistry. And a carbon involved with 4 single bonds, just a bit of review here, would be tetrahedral in its geometry. So hopefully you remember molecular geometry, the Vesper theory. when we're looking at the valence electron repulsion theory. Carbon with 4 single bonds would have tetrahedral geometry. It would also be sp3 hybridized. We're going to talk about hybridization in the next lesson. A carbon involved in a double bond would have a trigonal planar geometry because it would only have 3 things around it. Now, these here are just general structures. These carbons would need other things attached to them. But if they had a double bond and 2 single bonds, they would be trigonal planar in geometry and sp2 in hybridization. A carbon that's involved in 2 double bonds or a triple bond would have linear geometry. And when we get there, we would have sp hybridization. So carbon, particularly in organic compounds, is found to have covalent bonds. There's not a whole lot of ionic bonding going on in organic chemistry, which we did see quite a bit of in general chemistry. So if we want to take a look at some of the common organic chemistry atoms, because there's quite a few, some of the most common bonding partners for carbon include hydrogen, oxygen, nitrogen, and the halogens. Now hopefully everybody realizes that hydrogen just has the 1 electron. It's the simplest of the elements, and therefore its Lewis structure would just be hydrogen, and then we would have 1 dot by it. But let's take a look at some of the others. What are the Lewis structures of the most common organic atoms that we tend to use? Halogens, which you hopefully remember, fluorine, chlorine, bromine, and iodine, are in group 7A, and they take on this structure here. They've got the 3 pairs of lone pairs of electrons for a total of 6 electrons, and then they have that 7th electron that is an unpaired electron. So the halogens can only form 1 bond, kind of like hydrogen. Oxygen can form 2 bonds. We have 2 unpaired there. It's in group 6A, and it has 2 Lewis pairs. And then we have the lone pair on the nitrogen here. That can form 3, so that's getting closer to carbon. And then finally we have carbon that could form 4 bonds, and that's usually the center atom. And so that is pretty much going to wrap up our first lesson here on what organic chemistry is and why carbon is important. So hopefully you realize organic chemistry is the study of chemistry in living systems. Living systems tend to have a lot of carbon-containing compounds, and so we really define organic chemistry based on carbon. And then we also take a look at some of the bonding, the valence structures. You hopefully understand some of that now. And we also took a look and review of the basic structure of an atom. So that was stuff from general chemistry as well. So thank you, and as always, please continue to keep learning, whether it's here or elsewhere. You want to be investing in yourself and in your mind, your education. Thank you for watching. Please remember to like the video if you found it helpful. You are welcome to comment, and I will try to get back to those comments. And then you would, I would suggest that you should subscribe, because it's going to be the quickest way to find out when new videos are posted. You can also sign up for playlists and things like that that'll just cycle through and teach you organic chemistry. So thank you very much, guys. Please check out my other videos, and I will see you for the next lesson when we talk about hybridization of carbon.